What if there was such a thing as negative mass? That would be quite a weird phenomenon. Gravity would be repulsive rather than attractive, and objects wouldn't move like we expect them to. And whilst we've never observed such a strange thing happening, the physics certainly doesn't ban it. Well then, let's find out more. I'm going to start this little journey by answering the question, what is mass to begin with? Well, whilst that might seem like a really simple question, the answer is anything but simple. So I'm going to break it down in a number of stages. So put very simply, mass is the quantity of matter that makes up a given object, like a rock or a star. But let's delve deeper. So generally there are two concepts that are both thought of as mass. The first is inertial mass. This is how much an object resists being pushed, or how much do I have to push an object to get it to move, or to slow down or speed up an already moving object. Newton's second law tells us about this type of mass. More mass on this side of the equation means more force needs to be applied on this side of the equation to get an object to accelerate. The second type of mass is gravitational mass. This is how much an object feels gravity, and how much gravity it produces as a result of its mass. In Newtonian gravity, the gravitational force between two bodies has a function of their mass as can be seen here, and I'm sure we all know that more massive bodies create a greater gravitational pull. Okay, great, so that's told us what mass does, but hasn't really told us what it is. For that we need to go a little deeper. Objects are made of atoms, and those atoms are made of protons and neutrons and electrons, and inside the protons and neutrons are even smaller particles called quarks. And these particles are held together by a force called the strong force. And this force holds a lot of energy. And as we know from Einstein's equation, energy is mass. And so most of the mass of protons and neutrons comes not in fact from the mass of the quarks inside, but from the energy of the strong force. So that accounts for a lot of the mass of particles. But what about the mass of the particles themselves, like quarks? Where does that come from? And as usual, it's about to get a bit quantum. Particles are just fluctuations in the quantum fields that pervade all of reality. Electrons are fluctuations in the electron field, quarks are fluctuations in the various quark fields, and so on. And this is where the Higgs field comes in. According to the standard model of particle physics, some of these particles interact with the Higgs field, and that interaction slows the particle down and gives them inertia. And this is what we know as mass. Particles that interact with the Higgs field more have more mass, and some particles like photons don't interact with it at all and have no mass. But here's the interesting thing. None of this says that the mass has to be positive. So what about negative mass? And what would it look like? So come with me as we embark on a couple of thought experiments to explore just what negative mass would look like. And I'm not breaking the physics here. In Newton's laws, I can just plug in a negative number for mass and nothing breaks. It just gets weird. But we like weird, so let's go. So first, let's consider inertial mass. And here's the equation for Newton's second law again. Let's rearrange it so this will give me acceleration. If you look at the wording of the law, it states that the change of motion of an object is proportional to the force impressed, and is made in the direction of the straight line in which the force is impressed. Now, for normal masses, if I apply a force, this will give me an acceleration in this direction. Now let's plug in a negative number for the mass, and suddenly the acceleration is happening in the opposite direction. As I push the object in this direction, there's an acceleration happening, but it's in the direction against the push. So as I push the object in this direction, it'll accelerate back towards me. It's like the object wants to cancel out the force I applied to it. Like I said, weird. But it gets weirder. Let's now think about gravity. If I have two positive masses like shown here, the positive mass here attracts this positive mass, and this positive mass also attracts this positive mass here. And this is generally how we understand gravity work in very simple terms. Well, let's try that with two negative masses. Here it's starting to get weird. Here is the equation for Newton's law of universal gravity. And if I have two negative masses, the magnitude of the force is positive, just like if I had two positive masses. This therefore means that they experience an attractive force. However, because the inertial mass is negative, the direction of the acceleration is flipped. In other words, if we look at object 1, it feels a force towards object 2. But just as in our first thought experiment, the direction of acceleration is in the opposite direction to the force, and so it accelerates away from object 2, and object 2 does the same. This means that the gravitational force is still attractive, two negatives make a positive, but because of the negative inertial mass, the movement is in the opposite direction to the force. I did say weird, it's about to get even weirder. Let's get a negative mass here, and next to it let's put a positive mass. Now, the positive mass attracts everything, even a negative mass. But the negative mass starts to accelerate away from the direction of the force. But since the positive mass is attracted to the negative mass, they start to accelerate together. And they accelerate together forever, without the need for any fuel. And this setup has a name. It's called the runaway motion problem. And whilst it doesn't break any of Newton's laws, it is quite suspicious and really weird. Okay, so far we've played around with Newton's laws. But what would Einstein have to say about negative mass? Well, first of all, according to general relativity, gravity isn't a force at all, but the curvature of space-time caused by mass or energy. Matter tells space-time how to bend, and space-time tells matter how to move. And again, Einstein's equations don't forbid negative mass or negative energy. Positive mass bends space-time inwards, a bit like a heavy object being placed onto and bending a rubber sheet, but in 3 dimensions. A negative mass would bend space-time outwards, a bit like pulling the rubber sheet up into a hill. This space-time hill would push other objects away, like rolling down a hill away from the source of negative mass. And here's where it all gets very strange and very speculative. Negative mass could lead to negative energy densities, and that's something that general relativity doesn't like. According to general relativity, the energy density of a region of space cannot be negative. However, we're still in speculation territory, and negative energy density could be the key to some truly bizarre physics concepts. It could lead to warp drives, like the Alcubierre Drive. This involves compressing the space in front of a spaceship and expanding it behind the ship. This would then allow a spaceship to travel faster than light without breaking relativity. Another way of travelling from one space to another is by the use of wormholes. These would need to be kept open, and one way of doing that is by using some kind of exotic matter with negative energy. Possibly the most strange is the Krasnikov Tube, a stable wormhole which travels both in space and time. And by using 2 Krasnikov tubes, it would be possible to construct a time machine. Very strange indeed. So we've seen how negative mass behaves and how it could be used in strange and useful ways. But the big question is, could it actually exist? Well, so far no one has actually observed negative mass directly. All the particles that we know of all have positive masses. But some physicists wonder if we're looking in the wrong place. Right now, the universe is expanding faster and faster. Something that we've called dark energy is pushing galaxies and galaxy clusters further and further apart. Some scientists are now even questioning if dark energy exists at all. But what if that expansion is just the large-scale effect of negative mass? If enough of it was scattered throughout the universe, its repulsive gravity might explain the expansion that we see. There are also hints in the world of the quantum. The Casimir effect occurs when two uncharged parallel plates in a vacuum attract each other due to the fluctuations in the quantum field between the plates. Some interpretations of this effect involve the creation of regions of negative energy density. Even if negative mass doesn't exist in nature, it still teaches us something useful. It shows how the rules of physics are connected, how flipping one thing, a minus sign, can unravel everything we thought we understood. It also reminds us that the laws of the universe aren't sacred. They're descriptions, not commandments, and we can play with them. That's how we got general relativity, quantum mechanics, and yes, warp drive equations. Whether negative mass turns out to be real or not, the idea pushes science forward. It cracks open the door to what might be possible. Because sometimes to move ahead, you have to imagine what happens when you push and the universe pushes back. But for now and until next time, thank you for watching.